Welcome back. Today we start talking about section 14.5, the chain rule. Of course, we're still dealing with multivariable calculus, still dealing with multivariable functions. Let us first recall the chain rule for functions of single value. If you recall, guys, the chain rule gives the rule for differentiation of a composite function. For example, if y is f of x and x is g of t, and f and g are differentiable functions, then y is indirectly a differentiable function of t. And you can say that dy over dt, so if you plan to differentiate y with respect to t, you will finally get dy over dx multiplied by dx over dt. Okay? Well, as a matter of fact, these two, they cancel each other, and you get dy over dt. So for functions of more than one variable, the chain rule has several versions, each of them giving a rule for differentiating a composite function. So let's see what we have. So the first version, in fact, the theorem 2 in the book, deals with the case where z is a function of two variables, x and y. And each of the variables x and y is in turn a function of a variable t. Okay, so this means indirectly that you have a function of t where z is f of g of t, h of t. Okay, and the chain rule gives a formula for differentiating z as a function of t. So of course we assume here that f is differentiable. So let's see what we have. The first case, case 1. So let's recall that this is the case when f of x and f of y, so the derivative of f with respect to x and the derivative of f with respect to y, the first partial derivatives are continuous. Okay, so if they are continuous, it means that f is differentiable with respect to x and y. So the case 1 of the chain rule, we suppose that z is a function of the two variables x and y, is a differentiable function of x and y, where x is equal to 0 of t and y is h of t, are both differentiable functions of t. Then we say that z is a differentiable function of t, and we can write it this way: dz over dt is in fact differential f over differential x times dx over dt plus differential f over differential y times dy over dt. Okay, so you end up with dz over dt as differential f over differential x times dx over dt, okay, plus differential f over differential y times dy over dt. And since we often write dz over dx in place of df differential f over the differential x, we can rewrite the chain rule in this form, in the form that dz over dt is dz over the differential z over differential x times dx over dt plus differential z over differential y times dy over dt. Okay, so this is the first chain, and we will see in practice what it would happen. So let's see with the first example here. Here we have z as x squared y plus 3y to the power 4, 3xy to the power 4. So, and we have x equals sine 2t and y equals cosine t. So the question here is to find dz over dt when t equals to 0. So if we use the chain rule, what do we have? We have dz over dt is differential z over differential x times dx over dt plus differential z over dy times differential times dy over dt. Okay? So first of all, let's compute these parts. What is dz over dx? I mean, the derivative of z with respect to x here. Of course, it will give you like z and xx, which equals 2xy plus, from the second hand here, you get dy4. Right? So this is, as you see here, between brackets, it's z and xx. So it's the derivative, first partial derivative of z with respect to x. Then, and the next item here, which is dx over dt, what is? It's just the derivative of x with respect to t. So, of course, since you have sine 2t, the derivative with respect to t would be 2 cosine 2t. Okay? So this guy is dx over dt. Okay? So the next part, now we are talking about this guy, x squared plus 12xy cubed, as the derivative of z with respect to y. Of course, since you had here z equals x squared y plus 3xy4, zy, we've seen it before, is going to be equal to x squared plus 4 times 3, which is 12, xy to the power 3. Okay? So this is what you got here. Okay? And the last part, which is dy over dt, the derivative of cosine t, y is cosine t. With respect to t, of course, you're going to get minus sine t. This guy is dy over dt, which is minus sine t. So as you see, now it's necessary to substitute the expressions for x and y now in terms of t. So it's not enough here. We cannot return this derivative in this format. We have to convert the x and y to their expressions with respect to t. Okay? So we have to plug here, instead of x, we have to plug sine 2t, and instead of y, we have to plug cosine t. Okay? Of course, you end up with trigonometric form of the derivative of z with respect to t. Okay? So let us now simply observe that, in fact, the question, it was about the evaluation of this derivative where at t equal to 0. So at t equal to 0, what happens, in fact? You can get it right away. You can just plug in here what happens at 0 for sine. You're going to get to 0 for sure. So it doesn't matter what you have in front, you're going to get to 0. And the 2 cosine is going to be equal to 2. And all you have to compute is 2xy plus 3y4. So you see that the 2x anyways, when t equals to 0, you're going to have a 0. Okay, so x is 0 at t equals to 0. Okay. So that part goes away. And the 3y4, in fact, y is how much? Y is 1, because cosine of 0 is 1. So you get 3 times 1 to the power 4, so just 3. 3 times 2, you should end up with 6. Okay? So this way, you see with the substitution now at t equals to 0, what you got here is 0 plus 3, as we just explained, times 2 cosine 0, plus 0 plus 0 times sine 0, which is f(x). So you end up with the value of the derivative at 0. Is that okay for everyone? Is it clear for everyone? Any question?
Clear.
Clear? Okay. So let's move forward and see now what happens maybe with more complicated cases. Okay? So we consider the situation where z equals f of xy, but each of x and y is a function of two variables, s and t. So now we have x and y, not single variable functions by themselves, but two variable functions also. S and t, two variable functions. So S and T are two different variables. So now Z will have a derivative with respect to S and a derivative with respect to T. So Z indirectly is a function of S and T, and we would like to find these two derivatives. So now let's recall that in computing dz over dt, or differential z to differential t, we hold S fixed, constant, and compute the ordinary derivative of z with respect to t. So we'll do just a similar thing. So therefore, we can apply, in fact, the previous theorem, and we obtain the following. So first of all, dz over differential z over differential t is differential z with respect to x times dx over dt, and plus dz over dy times dy over dt. Okay. So this is for the first part, and now what is remaining is just if you plug here instead of t s, you end up with the second formula, and you end up with this formula for the derivative of z with respect to s. you just change the s by t or t by s, you get two similar forms. Okay. So in the second case, in the case the two variables x and y are themselves functions of two variables s and t, what you can do to find the partial derivatives of z with respect to s and t, you just plug in the same rule we've seen in the previous in the chain rule case 1. So dz over ds is dz over dx times dx over ds plus dz over dy times dy over ds. Or you can write it also when it happens, you can say it in d or differential, doesn't make any difference in fact. So we can say it's dz over differential z over differential t equals differential z over differential x times differential x over dt plus differential z over differential y times dy. So you see that the case 2 of the chain rule contains three types of variables, s and t, which are in fact at the end of the day they are independent. X and y are intermediate variables because they are used to just to find the value of the dependent variable, which is okay, just for terminology point of view. Okay, so this is like a kind of a diagram, a tree diagram. This is z, and you want to find the partial derivatives with respect to x and y. And each of these, in fact, when you consider that x is a function of s of t, you end up having two partial derivatives also for x. First partial derivatives, one with respect to s, the other one with respect to y, one with respect to x, the other one with respect to y. Okay, got it? Okay, so this is like, I mean, a diagram to follow to organize your work how it should be. Okay? So this slide is just to explain what's going on with the diagram. I think it's pretty obvious to get this. So let's see the general form, okay, before going maybe into more practical things. So the general form, if you have a function u, which is expressed using n variables from x1 to xn. So now we are not considering x and y alone. Just suppose that u is a function, in fact, of n variables x1 till xn, and each one of these is by itself a function of m other variables, let's say with index t with index going from 1 to n. Okay. So you end up, if you want to find the derivative of u with respect to ti, as you see, you're gonna just have to find the derivative of u with respect to each one of these x variables first, x1, x2 till xn, and multiply each one of them by the derivative with respect to the corresponding ti. Okay, so you write it this way. So you end up with kind of how many you have at the first level. This is u. At the first level, you have how many kinds of derivatives? You have first partial derivatives with respect to the xi's. You have n derivatives, n first partial derivatives, and each one of them has possibly m partial derivatives with respect to the ti's. Okay? Right? Got it? So you end up with a huge number, of course, of first derivatives with respect to each one of these. So that's the general pattern. Okay? So let's see an example before moving forward. So let me go back to this slide, and let's see an application to this. If you allow me, I'm going to take the textbook, and we're going to look for a question that is relevant in this context. So I'm in the book. If you have it with you, it's going to be helpful. If not, it's okay. So I'm taking the book. I'm taking exercise 5, example 5. Let me share with you my whiteboard, okay? So I'm taking example 5. So let's work it together, first of all. Page 941. Okay. So example 5, page 941. It says that u here is equal to x to the power 4y plus y squared z cubed. Okay. Now, what do we have on the other hand? We have x as a function of s and t is equal to r s e to the power t minus t, sorry, not t, just t. This is y, which is to the power minus t. And you have y equals rs squared e to the power minus t. Okay. And finally, the z, which is equal to r squared times s and times sine t. Sine t. Okay. So, of course, you need to understand that we do have the first layer here gives first and three intermediate variables, which are x, y, and z, are intermediate variables. They are intermediate variables. And the independent variables, they end up to be how many? R, S, and T, okay? And R, S, and T are independent variables. Independent variables. Okay. Now, what is the question? We would like to find differential u over ds over differential s. Its value when r equals 2, s equals 1, and t equals 0. Okay. So let's do it together first. Okay. Is the question clear, guys? Oh, okay, all right. Then let's go ahead. So first of all, you see that we need to compute the derivatives of all the intermediate variables here, y, x, y, and z, with respect to whom? With respect to this guy, s, right? Okay. So we'll write down that differential x with respect to s first of all. How much is it? You have the s is just as a constant here. Okay, so you it's just a multiplier for RET. So you end up with a derivative with respect to s, which is RET. Now the derivative of y with respect to s is going to end up being equal to here. This is s to me, so it's going to be 2r s e minus t. All right. And finally, you have the derivative of z with respect to s, which is how much, guys? It's r squared sine t. Is it okay with you guys?
Yes.
So these are the first partial derivatives of x, y, and z with respect to s. Now, we are going to use them here in differential u with respect to s. Before that, we need the derivatives, first partial derivatives of u with respect to x, y, and z respectively. Okay? So let's compute them on this side, okay, of the board. On this side of the board, I'm gonna plug in the derivative of u with respect to x. First of all, is going to be equal to how much? It's 4x cubed y. And that's it. Now, the derivative of u with respect to y is here. I'm going to have x4 plus how much is 2y z cubed. Am I right? And finally, I have differential u with respect to z. Is going to be just one item. It's 3y squared here, sorry, and it's z squared. So I'm done. Now I have all 6 first partial derivatives I need. First of all, the first layer is are the first partial derivatives of u with respect to x and y and z respectively. Then for each one of these intermediate variables x, y, and z, I need the derivative with respect to s. Okay? This way I have the my chain rule ready to go. Okay? So now what is much easier to avoid any confusion instead of writing a huge formula? Okay? Now all I need is to plug in these values, so I'll end up finding my result without, entering into too much details. Okay? So maybe you see, organization, guys, organizing your work is most of the time the most important thing. Okay? So let's compute these values at 2, 1, and 0. How much is that, guy? RET here. I'm going to have 2. E of 0 is 1. Am I right? Yeah. So this guy now, dy over ds at r equal to s equals 1, t equals 0 is going to be 2 times 2, 4 times 1, and again e of 0. Okay, so I'm going to have 4. And finally, r squared sine t is going to be 4 again. 4 again, but sine of 0 is 0, so it's going to be 0. Okay? Was in fact, it's a good news to me because it hits this guy, it's going to be a 0. Now, for these values, I'm going to determine how much is x and y before looking for the values here. Okay? Now, what happens with the value of x at r equals 2, s equals 1, t equals 0? This guy at this point is equal to 2.
2 times 1 times.
Right? Yeah, and you have r s squared, so it's 2 times 1 times 1. Okay, and finally, here I'm going to get 0, right? Okay, so you know that at this point now, x equals 2, y equals 2. Okay, so I'm all set. Now I can compute these values at exactly r equals 2, s equals 1, t equals 0. So I'm going to have this guy, du over dx, is going to be equal to 4 times 8, times 2, times 2. Okay? 4 times 8, 32 times 2 is 64. And finally, this guy is equal to 2 to the power 4, which is 16. 16 plus the 2y is how much, guys? Y is 2 times z is 0. So it's just 16, okay? So I'm all set. I don't need this guy. Well, in fact, the good news is going to be also equal to 0, okay? So you can just plug it here now. You're going to multiply the 64 by how much? So it's going to be equal to 2 dx. Yeah, it's going to be equal to du over dx times dx over ds. So it's 128. Okay, plus the 16 times the 4. So it's 16 times 4 is 64, am I right? Okay, so you end up with the following. I think it's 190. 190. Okay, got it? Yes. Okay, any question on that, guys? So you see we had to find first how many first partial derivatives, the 3 derivatives of x and y and z respectively with respect to s, and on the first layer we needed to find the derivatives of u, first partial derivatives u with respect to x and y and z. Okay, of course at a given point which is r equals to s equals 1 and t equal to 0, we needed to find the first partial derivatives of their values. Okay, the values of x and y and z, and plug them in there, the derivatives of u with respect to x and y. Okay? So you see, it's just a matter of organizing your work. It's a matter of organizing your work. In fact, if you can plot a diagram of what we did, just to make it clear for everyone. So we had, what did we have at the beginning? We had u here. The first layer, we differentiated this u with respect to whom? With respect to x, yes. With respect to y, and with respect to z. Yes? Of course, each one of them needs to be differentiated with respect to s, y, and t, but we've taken only that part that corresponds to what we need. Okay? Of course, each one of them will be differentiated with respect to s, r, s, and t, but we've taken just the derivative with respect to s. Okay? Any question on that, guys? Is it okay? Okay.
Yes, clear.
Okay. Okay. So let's see probably a more complicated question, a little bit more theoretical one. So here I have g of x. So this is example 6 of the book, page 941 also. 941. And I do have a g of st, which is equal to g of st to f of s squared minus t squared and t squared minus s squared. Okay. Where f is differentiable. Okay. All we know is that f is differentiable. Now, we'd like to show that this function g satisfies the fact that g, sorry for that. Oh, what did I do? Okay, we'd like to show that, I'll write it again, okay? So I'll like to show that t times dg over ds plus s times dg over dt equals 0. Okay. In fact, we had g of st. So probably you can see right now that you need to compute the derivatives of g with respect to s and t, and you plug it in. S squared minus t squared, and the other one is just the opposite. Okay. So let's go. So what is the idea? We need to find the derivative of g with respect to s, first of all. So that was example 6, same page as previously. Page 941. How much I'm going to have? So what does the formula say? It should be the dg, okay, with respect to over df over dt. Am I right? Over ds, sorry. Okay. Is that okay with you guys? You get this?
Yes.
Okay. So what is the derivative, in fact, of f with respect to s here? What am I get? I'm going to get. Whatever happens here. With respect to s. To s only. So assume here, guys, just for clarity, assume this guy is x, okay? And this guy is y, okay? So they are hidden here, okay? So if we were to use the chain rule, we would have written the following, right? Am I right? Because y is also carrying s. Am I right, guys? Is that clear? Okay, so now let's compute them. It's much easier. So now df over dx. What is the derivative of f with respect to x? You don't know the expression. You don't need it. Okay? But still, now you need to compute the derivative of x with respect to s, which is 2s. Got it? Plus df for dy times minus 2s. Am I right? Okay. Yes? Am I right, guys?
Yes.
Okay. So if you plug this guy now, plug it here. Let's go backwards. I'm going to have dg over df times, what am I going to do? I'm going to plug df over dx to s plus, sorry for that, df over dy minus 2s. Okay? So what's going to happen here? I'm going to have do you see something, guys? Go ahead. So I'm about to compute this guy.
Okay.
Okay? So you see that yeah? Should I leave it like this? Or can I remove the differential f, if you wish? Okay? I'm going to remove the differential f, okay? From here, above and down. So you can write it as, in fact, as a matter of fact, that was the first part. You can write dg over ds as dg over dx times 2s minus 2s times dg over dy. Okay. So this is the first part. Okay. Now the second part, if you do the same, you're going to have the dg over t. It's quite similar, guys. So again, avoid the details. You're going to have equal to dg over dx times minus 2t. It's just differentiated with respect to t now. Plus dg over dy times 2t. Okay? So let's see what happens. I'm going to use a different color. So if I use a different color, what happens if I multiply the first guy here by t, as it's said in the equation? I multiply by t, I'm going to have t times this, so it means I'm going to have minus 2st times dg over dx, okay? And I'm going to have t also here, okay? And if I multiply this guy here, dg over dt by s, I'm going to have the same, which happens here. So if I sum up, you see that the dg over dy times 2st goes with dg over dy minus 2 times minus 2st, and the dg over dx times minus 2st will go with dg over dx times 2st. Okay? And this way I'll get the zero check. You got it, guys? Okay. It's a little bit so it's a little bit tricky, but still maybe here I'm choosing the way which is more simple. I use these intermediary variables, the x and y. In the textbook, they are not using it, they go back to that. Okay. So this is for the for two questions on separate questions on the channel. Okay. So let's get back to our things, to our file here, and I'll continue now with implicit differentiation. So if you recall, guys, one part of calculus 1 was on implicit differentiation. When do we have to use implicit differentiation? When, for example, we don't have an explicit expression of our function. Okay, but still we need to determine the derivatives. So, in fact, the chain rule here is a useful tool that can be used to give a more complete, in fact, description of the process of implicit differentiation. So suppose that an equation of the form f of x y equals 0 defines y implicitly as a differentiable function of x. That is, in fact, y is a function of x, but maybe you cannot retrieve it. But capital f of x is equal to 0 for all x in the domain of f. Okay? Just to map the equation, in fact. So if f is differentiable, we can apply case 1 of the chain rule, one that gave, in fact, the partial derivative of f with respect to x for the first independent or the independent variable t, and we can use it to map, in fact, that for both x and y, we can obtain that differential capital F over differential x times dx over dx, which in fact at the end of the day is 1, plus differential f over differential y times dy over dx is equal to 0. Okay? So we can use it to map this and to solve, to find the expression of the derivative. So at the end of the day, what we have, we can decompose it, and we can write that differential y over differential x, which is the intention. We need to find this. We can write it as minus differential capital F over differential capital X over differential capital F over differential capital Y. And if you just use the different notation, you can write it as minus first partial derivative with respect to X over first partial derivative of capital F with respect to Y. So to derive this equation, we assume that capital F function was equal to 0, and it defines Y implicitly as a function of X. Okay? So this is the implicit function theorem, in fact. So let's see what we have as an application to this. So for instance, here we have x cubed plus y cubed equals 6y. Okay? And the intention is to find this guy, differential y over differential x. Okay, got it? Of course, here you cannot probably isolate x from y. So you cannot write y as just a simple expression of y with respect to x, because you need to solve, in that case, a third-degree equation. So what do we need here? We need to define this capital F function. So we define f of xy, capital F of xy, as x cubed plus y cubed minus xy, of course, which equals 0, in fact. As a matter of fact, if you are satisfying the equation, you end up with 0. Now, if you follow that theorem, we have dy over dx that could be written as minus capital F of x over capital F of y. I mean, the first partial derivatives of capital F with respect to x and y. So all we need to compute are the first partial derivatives of this function. So we get 3x squared minus 6y, of course. This is the derivative with respect to x. And the second one, the derivative with respect to y, would be 3y squared minus 6x. And this is what is written here. Okay? So at the end of the day, what do you have? You have the expression of the derivative of y with respect to x, even though you don't have y explicitly as a function of x. Got it, guys? And in fact, if you recall, we did a similar thing with calculus 1. In calculus 1, we did a similar thing to get the first partial derivative or the derivative, even though we didn't know the expression of y with respect to x. Is that clear, guys?
Yes. Doctor,
Yes.
does it work the other way around? Like if I want dx, it will be capital Fy over capital of x?
If you want the derivative of x with respect to y, yes, of course, it should work the other way.
Okay.
Yeah. So in fact, here we suppose that we do have what? We do have just two variables, okay, x and y. So let's now suppose that z is given implicitly as a function of f of xy by an equation of this form, f x y and z, like for example the equation of a plane, if you wish. So this means, in fact, that you have capital F x y, and here you plug in z. You see, equal to 0. Okay. So for all x and y in the domain of f. So if capital F and small f are differentiable, we can use the chain rule to differentiate the equation capital F of x, y, z equals 0 as follows. Okay. So we write the first partial derivative of capital F with respect to x, and we decompose it as the sum of these first partial derivatives products, and we can and recall that these derivatives are 1 for the derivative of x with respect to himself, 0, dy over dx is 0, and so this becomes in this form, d capital F over dx plus d capital F over dz over dx. Why is that supposed to be equal to 0? Because we are assuming here that y is not related to x, but in fact z is the variable that is related to x and y. Okay, just for clarification. So if the derivative of f with respect to z is not 0, we solve easily for dz over dx and obtain the first formula in the previous equation. So the formula dz over dy is obtained in a similar manner. Okay? So in fact, you get something which is quite similar to the implicit differentiation first formula we got. Dz over dx, you can write it as minus capital F with respect to x over capital F with respect to z, and dz over dy, you can write it as minus capital F over dy over capital F over z. Okay? So this way you get the a complete picture of the implicit differentiation in many cases. So let's close with a simple problem where we have an application to this. So I'm closing with example 9 from the textbook, which is in page 943. And in this case, guys, what do we have? We have x cubed plus y cubed plus z cubed plus 6xyz equals 1. Okay, so this is the equation. So what do we need to find? We need to find dz over dx and dz over dy. This is what we need to find. Okay? So we use just what we just shown, we said that dz over dx is equal to minus capital F with respect to x over capital F with respect to z. This is what we wrote. Am I right? Now, what is f of x, y, z here? From that equation, we should first of all extract the way the function capital F is written. It should be, which equals 0. Huh? It should be equal to x cubed plus y cubed plus z cubed plus 6yz minus 1 equals 0. Okay? So now you can plug in the derivatives. The derivative with respect to x here is going to be easy. It's 3x squared plus 6yz, right? But the derivative with respect to z is also easy, 3z squared plus 6xy. So this is the first one. All right? Now you can simplify by 3 if you wish, and you end up with x squared plus 2yz divided by z squared plus 2xy. So that's the first guy. Now, the second guy, dz over dy, you can write it as, follow the pattern, minus capital F over y here should be, over capital F over z. Okay? The only difference here is that you're going to change the numerator. You're going to stick with the minus 1. Here you place the 3z squared plus 6xy. And here you're going to have 3y squared plus 6xz. Am I right? So we end up with a similar formula, which is minus y squared plus 2xz over z squared plus 2xy. Okay? So these are the derivative of z with respect to x and y. Okay? We are all set, guys. Okay? So, any question, guys, on that? Is that okay?
Clear.
Here for everyone? Okay, so that's it. So that's it for the day. Thanks for following. If you have any question, don't be shy to send any message. I will post that video and send you the link. Okay. Okay. Have a wonderful day, guys, and see you soon.